this episode, we'll talk about hypothesis testing. Hypothesis testing is one example of statistical inference. To make sense of data, we want to infer or draw a conclusion from a set of data. Most quantitative research studies use some form of hypothesis testing. So this is one of the most important topics we could learn. In hypothesis testing, we test a claim. For example, let's say our claim is that texting while driving increases the chance of an accident. Then we collect random sample of those who text while driving and compare this to a standard measure to see if the proportion of accidents from those who text is greater. Hypothesis testing is used to infer whether or not there's sufficient evidence to show that texting while driving significantly increases traffic accidents. If the data show that the number of accidents is not significantly different from the norm or falls within the margin of error, we say there is not sufficient evidence to make that claim. So hypothesis testing is a method we use to test a claim. We have two different methods. We have the traditional method and the p-value method. The methodology you employ depends on the technology used and the nature of data. When you finish a hypothesis test, you state the conclusion. We either say that you reject the null hypothesis or there is insufficient evidence to show that that claim is true. The best way to determine whether a statistical hypothesis is true is to examine the entire population. However, it's very difficult to get the data from the entire population, and so we use a random sample. The hypothesis is rejected when the data fall beyond the margin of error. In each question, you will have a null and alternative hypothesis. The null hypothesis, denoted by h sub 0, is the hypothesis that sample observations result purely from chance. The alternative hypothesis, denoted by h sub 1 or h sub a, is the hypothesis that the sample observations are influenced by some event that did not occur by chance alone or happened because of a non-random event. For example, suppose we want to determine whether a coin is fair and balanced. The null hypothesis is that half of the flips result in heads and half result in tails. The alternative hypothesis would be that the number of heads and tails is significantly different. Symbolically, these hypotheses are expressed as h sub 0 is p equals 0.5 and h sub 1 is p is not equal to 0.5. Suppose we flip a coin 50 times and we get 40 heads, 10 tails. You ask yourself, is it possible that 40 flips landing on heads is likely due purely from chance? Probably not. Given that result, we're going to reject the null hypothesis and state that the coin really wasn't balanced. Mathematically, this is how we conduct a hypothesis test. Statisticians follow a formal process to determine whether to reject a null hypothesis based on sample data. The process, called hypothesis testing, consists of 5 steps. First, state the hypotheses. This involves stating the null and alternative hypothesis. The hypotheses are stated in such a way that they are mutually exclusive. That is, if one is true, the other must be false. From the given significance level, determine the critical value. That's step 2. The significance level is generally given. If not, use 0.05. Look up on a table the value for the critical value. The common ones for z are given in this chart. Step 3. Draw a normal curve and use the critical values that you found to shade the rejection region. Step 4. Compute the appropriate test statistic and put it on the normal curve. There are formulas for different tests, those for proportion, t-test, z-test, chi-square, f-test. Interpret results. If the test statistic is located in the rejection region, there is sufficient evidence to show that the claim is true, or the event probably didn't occur by chance. If the test statistic is not in the rejection region, there is not sufficient evidence to show the claim is true, and we fail to reject the null hypothesis. Let's look at an example. The null hypothesis is that p is equal to 0.5, and the alternative hypothesis is that p is not equal to 0.5. We're saying that you have a 50-50 chance of getting a head or a tail. Since the alternative hypothesis is not equal, then anything significantly more or significantly less, we would reject the null hypothesis. We say this is a two-tailed test. The significance level in this test is alpha equals 0.05. which means there's a critical value at 1.96 and negative 1.96. So we have rejection regions on both sides. We shade the rejection regions and then we compute the test statistic. In order to do this, we know that there are 40 heads in 50 tosses. So n is 50, that's the total number of tosses. P hat is x over n, or 40 over 50, which is 0.8. We know that p is 0.5, so q is 1 minus p, or 0.5. The test statistic formula is z equals p hat minus p over the square root of pq over n. We get 0.8 minus 0.5 over pq, 0.5 times 0.5 over n, which is 50. When we compute that, we get a z-score of 4.24. Notice that 4.24 lies in the rejection region because it's beyond 1.96. We say there is sufficient evidence to show that tossing a coin did not occur by chance and the coin is not balanced. The wording may seem strange, so let's answer this question. Can we really accept the null hypothesis? Some researchers say that we can either accept the null hypothesis or reject the null hypothesis, while other ones vehemently say that all we can do is accept the null hypothesis or fail to accept the null hypothesis. Why the distinction between acceptance and failure to reject? Acceptance implies that the null hypothesis is true, but it may not be. However, fail to reject implies that their data is not sufficiently persuasive for us to prefer the alternative hypothesis over the null hypothesis. So here are the steps. 1, state the null and alternative hypothesis. 2, choose a significance level. If it is not given, use 0.05 and find the critical values. 3, draw a normal curve, putting the critical values on the normal curve and shading the rejection region. 4, calculate the test statistic and determine whether or not the test statistic is in the rejection region. 5, state the conclusion. We could also do this by the p-value method. The strength of the evidence in support of the null hypothesis can be determined by the p-value. If the p-value is less than the significance level, we reject the null hypothesis. An easy way to remember that is if p is low, the null will go. One-tailed and two-tailed tests. A hypothesis test in which the rejection region lies only on one side, we call that a one-tailed test. For example, suppose the null hypothesis states that the mean age of students in this class is 25 and the alternative is that the mean is greater than 25. The rejection region would consist of a range of numbers located on the right side of the sampling distribution. That is, a set of numbers significantly greater than 25. In a one-tailed test, where we're looking for the average age is greater than or significantly more than 25, then we're only looking at one side. So if we're looking for an average age significantly more than 25, we're only looking at the one side, and we call this a one-tailed test. A hypothesis test in which the rejection region lies on both sides of the normal distribution is called a two-tailed test. For example, suppose the null hypothesis states that the mean number of trees in city parks is 100. If it is a two-tailed test, then the alternative hypothesis would be that the mean is either significantly less than 100 trees or significantly greater than 100 trees. In the example of the park, where we want to know whether there's significantly more or less than 100 trees, so we say that the mean number of trees in the park is not equal to 100 as our alternative hypothesis, that this is a two-tailed test. One sample tests are appropriate when a sample is being compared to a population. The population characteristics are known from theory or are calculated from the population. Two sample tests are appropriate for comparing two samples. Typically, these are experimental and control groups from scientifically controlled experiments, like, for example, clinical drug trials, with one group getting a treatment for acne and the other group getting a placebo. Z-tests are generally appropriate for comparing means that are normally distributed with a known standard deviation. while t-tests are generally appropriate for comparing means with small samples or larger samples when the distribution is not normal. Tests of proportions are similar to that of means, with using the critical value of z. Chi-square tests for variance or standard deviation are used to determine whether a normal population has a specified variance or standard deviation. F-tests in the analysis of variance, or ANOVA, are commonly used when deciding whether groups of data by category are meaningful. If the variance of test scores of left-handed students in an accounting class is significantly smaller than the variance of students in the school, then it may be useful to study left-handed students as a group. There are various types of hypothesis tests that you will use as you progress through the chapters on hypothesis testing. Well, that's all for now. Try some homework.